We experience the world as a place of definite states. A light is either on or off. But at the smallest scales of reality, this certainty dissolves into a sea of pure potential. This is quantum superposition. Before it's observed, a particle doesn't have a fixed state. Instead, it exists as a wave function, a mathematical description of every possible outcome at once. It is here and there. It is up and down. It is blue and red. This delicate dance of possibilities continues until the moment of measurement. The act of looking, of interacting with it, forces the universe to make a choice. The wave function collapses, and from the infinite possibilities, one reality snaps into focus. The quantum world's secret is that it's not what it is, but what it could be. Classical physics builds walls. If you don't have enough energy to go over a barrier, you're stuck. But the quantum world is a place of loopholes. Thanks to the Heisenberg uncertainty principle, a particle can momentarily borrow energy from the vacuum of space itself. This borrowed energy is enough to do the impossible. Pass through a barrier it should never be able to cross. It doesn't break the wall, it simply appears on the other side as if the wall wasn't there. This isn't just a strange theoretical quirk. Quantum tunneling is the very reason our sun shines, allowing protons to fuse together and power the stars. How does the bizarre nature of the quantum world transition to the familiar reality we see every day? In 1935, Erwin Schrödinger proposed a thought experiment to explore this paradox. Inside a sealed box, a cat's fate is tied to the quantum state of a radioactive atom. If the atom decays, a poison is released. If it doesn't, the cat lives.
Until I open it, the cat is both alive and dead. The wave function hasn't collapsed.
The most baffling part of the double-slit experiment is what happens when you watch. If you place a detector to observe which slit the electron goes through, the interference pattern disappears. The very act of measuring, of observing, forces the particle to choose a path. The wave of possibility collapses into a single definite reality, as if the universe itself knows it's being watched. What is the role of an observer in the universe? In our everyday world, looking at something doesn't change it, but in the quantum realm, observation is not a passive act. When we try to measure a quantum system to see which path a particle takes, we fundamentally alter the outcome. The shimmering wave of all possibilities which pass through both slits at once is gone. In its place is a single concrete particle, following a single predictable path. This is the observer effect. It raises profound questions. Does reality need an observer to become definite? What you're seeing here isn't science fiction. It's a real-world phenomenon called quantum levitation. By cooling a superconductor to extremely low temperatures, it can lock into a fixed position above a magnetic field, allowing it to float effortlessly. The object isn't just floating, it's locked in place by quantum forces. We're witnessing a rare glimpse of physics usually hidden from view. This is called quantum locking, a physical object held perfectly stable in midair, defying gravity. It serves as a stunning reminder that the rules of quantum mechanics can have powerful consequences on a macro level.
Quantum entanglement.
When two particles become entangled, they essentially behave as a single object. Even when separated by billions of miles, a measurement performed on one particle will instantaneously correlate with a measurement on the other. At the quantum level, our universe is connected in ways we're only beginning to understand. Quantum entanglement is the ultimate proof of this connection. It shows that particles can be linked in a profound way, sharing a single existence across any distance. It challenges our classical ideas of space and separation, suggesting that the fabric of reality is far more interconnected than it appears.